Welcome back. We want to proceed with our study on elliptic curves, and we had begun looking at Montgomery curves. We had just seen how to, in our last lesson, we saw how to convert the equation, the short Weierstrass equation to, if you are given the short Weierstrass equation, we show how to come up with the Montgomery equation. And vice versa. Also, if you're given the Montgomery equation, we saw how to come up with a short Weierstrass form. Of course, during that lesson, we emphasized that Montgomery form of elliptic curve is one of the elliptic curves that are used in real life situations. And so that is why it's necessary. If you have the short Weierstrass, you can convert it to a form that can be used in real life. So that is why we're doing all that. Now, so we also discovered that it was possible to convert every Montgomery form to short Weierstrass. It's possible to convert every Montgomery equation to short Weierstrass, but the other way around is not possible. That it's not possible to convert all of them, all the short Weierstrass forms to Montgomery. Only a few can be converted, and those that can be converted had to satisfy some three conditions. We went through those three conditions. Of course, one of the conditions was that for the short Weierstrass form to be convertible to Montgomery, then it had to have a number of points that are divisible by 4. That was one of the conditions, and it was the first condition we're looking at. Now, after looking at those conditions, we discovered that if the short Weierstrass form had 20 points, we would get also Montgomery equation having the same points, 20 points. So if it had 24, the Montgomery will also have 24 points. And so it's from this point that we now want to see how to transform the points of Weierstrass to the points of Montgomery and vice versa. Of course, we know that if the Weierstrass has 12 points, the other one will also have 24 points. So I want to see how do we transform the first point of short Weierstrass to another point of Montgomery, and how do we convert points of Montgomery to those of short Weierstrass, and vice versa, and so on. So that is what we'll be looking at today, transformation of those points. Of course, a point like the point of infinity, if it is in the short Weierstrass, it will still be mapped to the point at infinity. But these other points will be mapped. We want to see how they be mapped. But the point of at infinity will be mapped to the same point at infinity. Now, so I've said, the first point here I've said that the affine Montgomery coordinates, those points, creates a one-to-one correspondence with the points of the short Weierstrass, one-to-one correspondence. What that means is that if this is point A, let me talk of Montgomery and the short Weierstrass. If the Montgomery has point A, B, C, and this one has point E, F, G, what we mean is that this point of Montgomery will be mapped to only one point of the short Weierstrass. So every point will be mapped to once. For instance, this one could be mapped to here, this one could be mapped to here, and this one could be mapped to here. So this is a one-to-one correspondence. In other words, we cannot have one point being mapped twice. We cannot have point A here in the Montgomery being mapped to E and F at the same time. It can only be mapped to once. So that is why I say one-to-one correspondence. And again, this emphasizes a point we already mentioned, that the number of points in the short Weierstrass will be the same as the number of points in the Montgomery, so that we have one-to-one correspondence. Now, so that is what we will be doing. So we want to see how do we transform. Of course, we saw the formula for, we saw the equation for short Weierstrass. The formula for short Weierstrass was y squared will be x cubed plus ax plus b. And the Montgomery one was by squared was x cubed plus ax squared plus x. Now, so of course, we saw how if we are given this short Weierstrass form, we saw how to obtain b and obtain a. And of course, if you are given the Montgomery, if you are given this Montgomery equation, we also saw how to find a and how to find b. And of course, that is what I've just written here. What I've written here, that if you're given the Montgomery equation, you can find the a, this small a for the short Weierstrass, and the small b for the short Weierstrass forms. So if you're given the Montgomery, this Montgomery equation, and you want to get this short Weierstrass, the first thing you would do is to find a and b, respectively, small and small b. Now, using these parameters, this time, what we want to get x and y. So we want to get what x and y are. No, this is square plus x plus b. So this time we're not interested with this constants and b. We are interested with how do we find x and y, so that we can have points x1, y1. We can have point x2, y2, and so on. How do we find these values? That is our interest this time, and not the constants. But for us to get those x and y, first of all, we must find the constants. Must find the constants as we move forward. Now, I've been given Montgomery equation. I want to convert to the short Weierstrass. And what I'm interested in is the value of x and y. And the value of x will be given by this. And the value of y will be given by that. So that means x will be that, and y will be this. So that is how we'll be doing it. So it's very easy getting the y value, and it's very easy to get the x value. So for the short Weierstrass form, if you are given the Montgomery, and this is the formula we'll be using going forward. And of course, when you're writing the code again, if you're given the Montgomery, then you are telling this code to find the value of x and y for the short Weierstrass, and that code is using this formula, giving it this formula. So that means you give it b, you give it a for the Montgomery. For the Montgomery, you're giving it a and b, and then it will give you the value of x and y for the short Weierstrass. At every point, you'll be asking it. You want to ask for point 1, point 2, point 3, and so on. And it will be doing for you those points. Now, so what about if you're given the short Weierstrass and you want to get the Montgomery, the points of the Montgomery. So that means we just get the inverse the inverse of what we've just done. So that's why I've said that this transformation here, the transformation that maps a point of Montgomery to a point of short Weierstrass and gives you that this transformation has the inverse. So its inverse would then, the inverse means that this time you're given a point on the short Weierstrass, get the inverse of this point, and you get the other point. That gives you the other point, the point that this point will be mapped to on the Montgomery. So that inverse is what we then talking about. But now, before we get the inverse, we have to remember this. We called it the scaling factor last time. Call the scaling factor. And this the same way we did last time. We're getting, first of all, this 3 times Z naught, where Z naught is the solution to this. If you have to equate this to 0, Z naught is that solution. Now, that is a solution squared times 3 plus 1 plus A. Now, that means you've been given this. You have been given this is x naught, this square, x cubed plus ax plus b. So you have been given this equation for the short Weierstrass, and you've been asked to find points on the Montgomery. So you have to use this equation, therefore, to find a solution to this polynomial. If you equate it to 0, find a solution. And then that solution is square, and then add A. A is just coming from the short Weierstrass equation. The answer that you get a square root, and then the inverse of that square root gives you the scaling factor. Now, once you have the scaling factor, you can now calculate the points on Montgomery straight away. You can calculate the points on Montgomery, and the points are calculated using this formula. And what this means, therefore, you have a point on the short Weierstrass, and you want to find its equivalent, where it will be mapped to on the Montgomery. And so we are saying that this point that it will be mapped to, okay, this is the point on the short Weierstrass. Where will it be mapped to? On the Montgomery. Where will it be mapped to? So where it will be mapped to will be same as the S we've just calculated multiplied by X minus the solution we got after solving this polynomial. So this gives you the X value. This gives you the X value on the Montgomery. What about the Y value on the Montgomery? Will be the same as S times this Y value on the short Weierstrass. The same as that. So again, that is what you're giving your code. If you want your code to give you every point. So let me say you have this point on the short Weierstrass. You have this point on the short Weierstrass. You want to find where this point will be mapped to on the Montgomery. You want to find out where it will be mapped to. So you first of all calculate S, because you have the equation for the short Weierstrass. Using that equation, find S, find Z naught, then use it to find S. Then just come straight here. This point will be mapped to this S. Supposing our S is 8, let's assume our S is 8. Let's assume we're working in mode 17. So if our S is 8, then this point 2, 3 will be mapped to S, which is 8, multiplied by X. Our X in this case is 2. Then minus Z naught. The answer you got here. Let's assume it was 3. Let's just assume that it was 3, just for assumption. Then we, of course, we will do an exam. Then again, take the same S, 8. and multiplied by the y value, which is 3 in this case. Of course, you will reduce everything mod 17, and that gives you the coordinate that this is mapped to on the Montgomery curve. So those are the steps that we'll be using, so that if you're given a point on the short Weierstrass, you can always get the point on the Montgomery that this point on the short Weierstrass will be mapped to. So it's slightly related with what we were doing last time, because what we were doing last time, we just given a equation or Montgomery, and we are converting it to short Weierstrass. You're given a point on short Weierstrass, you're converting it to Montgomery, and so on. When we began, I already said that when you're mapping all these points, the point at infinity will remain the same point at infinity. So the point at infinity on the short Weierstrass will be mapped to the point at infinity on Montgomery. So this one does not require workings, but the rest of the points will require workings. Now, so let me look at this example, and I'm referring to the previous example. The previous example, we'd been given the short Weierstrass equation as that. And of course, we used this short Weierstrass to obtain Montgomery equation. So we in that previous example, we had been given the short Weierstrass, and we use it to get the Montgomery. Now, the question therefore is, okay, the points of the short Weierstrass are this. And the points of the Montgomery, when we did it last time, we found this. So this is a point at infinity. It will still be mapped to a point at infinity. I forgot to put it here. It's supposed to be a point at infinity here. Now, so the question is, what about this point? Where will it be mapped to? We cannot only say it will be mapped here. We cannot say that. Of course, we'll require to calculate to see where it will be mapped to. What about this? Where will it be mapped to? What about this? Where will it be mapped to? So that is what we want to see. That's what we want to see, where these points will be mapped to. That's what we want to see. What about the points on Montgomery? So where will this point be mapped to? Of course, we want to see whether it will be mapped there, whether this one will be mapped here, whether this one will be mapped there, and so on. So that is what we want to find out. Now, so if you're writing your code, therefore, you're writing your code, and you want to convert from Montgomery. So the only thing you have is this. You have the equation for Montgomery. You don't know the equation for the short Weierstrass. You have the equation for Montgomery. So then the question is, where will this point in the Montgomery, where will this point in the Montgomery be mapped to on the short Weierstrass equation? Or what is the equivalent of this point on the short Weierstrass? So, and you're using your code. So your code, since you have this equation, you're giving your code S, and then you're giving your code B. Of course, even S is not a must, but what is a must? You can calculate this S. You need to give it B and A. And then the field. So you see you're working on mod 17. So your code, after you've written it, you give it A, B, then give it the field. And then this is the point you want to convert to short Weierstrass. You also give it this point. Then after that, you give it the formulas. Give it the formula we've just mentioned above. How do you get a point? So you give it the formula here, that if you have the Montgomery and you want to convert to short Weierstrass, give it this formula here. So you're telling it You're telling your code that if you have this point on Montgomery, its equivalent on the short Weierstrass will be given by this. So it should be able to do that. It should be able to do that because you've already given it A, you've given it B, and you've given the point that you want to convert. So it just does that, and gives you the point on the short Weierstrass. Because when that time comes, I'll show you my code and you will see that is what happens. Now, what about if you're given the short Weierstrass and you want to convert to Montgomery? So what are you giving it? You're giving it this formula. You're giving it this formula for finding S, and then you're giving it the formula for finding the new point. So once, of course, you have been given the short Weierstrass, you've been given the short Weierstrass equation. So you're also giving it A and B. So that if it has A and B, it can come up with this polynomial and find Z naught. If you've given it A and B, it can come up with this polynomial. It knows what this polynomial is. Once you give it A and B, it knows what the polynomial is. And then using that polynomial, it will now get Z naught. Once it gets Z naught, you give it this formula to get S. Once it gets S, you have given it the point on the short Weierstrass, should be able to get a point, its equivalent point on the Montgomery curve. So I just want to go through one example, of course, how to calculate this. Then we go straight to the code and give it those formulas, and the code does for us. So this is the example I wanted to look at. We already have these points, and we just want to see how do we convert a point on the Montgomery to a point on the short Weierstrass. So we just take a point on Montgomery and insert it in our formula above. Insert that point in our formula. And this is our formula here. So I want to convert this first point to short Weierstrass. This is a Montgomery point. And the formula is this. This is the formula. So where there is, this is our X and this is our Y. So where there is X, I just put X, the value of X. And where there is Y, I put the value of Y. Of course, our Montgomery equation is just above here. Montgomery equation is our B is 15 and our A is 3. Our B is 15 and our A is 3. So B is 15. B is 15 and A is 3. So when you do this, of course, 3 times 0 will be 0, and then plus 3. Then out of 45, then 0 out of 15 will be 0. So this is the point you get. This is the point you get, which is same as 1 out of 15. But this point, you want to eliminate decimals. No, you want to do away the fractions. And we are working mode. We are working mode 17. We are working mode 17. So how do I do away the fraction? So what we have is like 1 times the inverse of 15, 0. So what is the inverse of 15? 1 out of 15 is the inverse of 15. So what is the inverse of 15 mod 17? because you're working mode 17. Of course, you can use your code to do it faster. To do it fast, you can use your code. But if you use the extended Euclidean algorithm, then you're asking yourselves, if 15 were to go here, what will be the remainder? And the remainder will be 2. And if 2 were to go into 15, what will be the remainder? The remainder will be 1. So you can now reverse this to find the inverse of 15. And when you do that, you get that the inverse of 15 will be 8. The inverse of 15 will be 8. When you do that, maybe I can just do it for the sake of recalling. For the sake of recalling, how do you find 8? So we reverse beginning with this first equation. We reverse beginning with this first equation. So 1 will be the same as 15 minus 7 multiplied by 2. So our second remainder, so this was the remainder, the first remainder, and then the other remainder, we're doing it from down going up. The other remainder is this 2, so we write its equivalent. So this will be 1 is equals to 15 minus 7. But this 2, the equivalent is 17 minus 1 multiplied by 15. So what do you get? This will be 15 minus 7 multiplied by 17. Then plus 7. I'm just multiplying. Multiplied by 15. This is equals to 1. Now, so collect leg terms. Collect leg terms. We have this will be the same as negative 7 multiplied by 17. And then this 15 and this are like terms. And that gives us 8 multiplied by 15. 8 multiplied by 15. So the question was, what is the inverse of, no, what is the inverse of 15? That was the question. What's the inverse of 15? And so the question is, using this equation, what number when multiplied by 15 gives you a remainder of 1? So the number which when multiplied by 15 gives a remainder of 1 is 8. Is 8, and that therefore 8 is the inverse of 15. Now, but all this we are doing it using your code, so we just again reminding ourselves how we do it using your code. The extended Euclidean algorithm. Now, so we've just seen that a 0.00 on the Montgomery curve would be mapped to 0.80 on the short Weierstrass. Of course, we had already said that the point at infinity will be mapped to a point at infinity. So we have no problem with that. But we have problems with the other points because we need to map all of them. But we're just taking 2 points as an example, convert as that you can do the rest. The formula is the same. Now I want to map 0.55. Let me just find out. 0.55 is on Montgomery, yes, this point. So the first thing we've seen this point 0, and the Montgomery has been mapped to 0.80. Has been mapped to 0.80. So you cannot easily tell where it's mapped to until you calculate. So you can imagine if you had a very big field, if you had a very bigger field, you're dealing with a very big prime number, then you cannot easily tell where that point will be mapped to. You can see where it has been mapped. It has been mapped here. So it was not automatic that the first point will be mapped to the first point. It's not automatic. What is automatic is that the point at infinity will be mapped to a point at infinity. But the rest of these other points is not automatic. So let's see where this other point, the second point will be mapped to, which is 5, 5. So again, we just go to the equation and insert the point. So this is our equation. If you're given a point on Montgomery, you can get a point on short Weierstrass using this formula. So where there is A, we had found that A was 3 and B was 15. So where there is A, putting 3, and where there is B, you're putting 15. And of course, you have the value of X and the value of Y. So the value of X, where there is X, you're putting 5. And where there is Y, you're putting 5. So once you've done this, what follows is now just simple arithmetic, knowing how to get the inverse and so on. So of course, the upper side will be 15 plus 3, which is 18 out of 45. And this other one is just 1 out of 3. And of course, this one you can also simplify. And you can see that a 9 goes here twice, 9 goes here 5. So you arrive at 2, 5, then a third as the point. This is the point, 2 out of 5, and then a third is the point. But of course, we are not dealing with the fractions. We know that we are doing mod 17. We are doing this mod 17. So this is the same as 2 times the inverse of 5, and then 1 times the inverse of a third, times the inverse of 3, mod 17. Mod 17. So you're asking ourselves, what is the inverse of 5 mod 17? In other words, what number, when multiplied by 5 and then divided by 17, the remainder will be 1. What number, when multiplied by 5 and the result divided by 17 will give you a remainder of 1. So that is the number we're looking for. So, okay, let me try 7. Of course, we are not trying, we are not using a trial, we are doing it by a Euclidean algorithm. Just want to try 7, looking at my answer, I want to see what, if it's 7. So 7 times 5, of course, that gives me 35. 35. Divided by 17 goes there 2 times. And what is the remainder? The remainder is 1. So 7 is this inverse of 5. So it means this will be the same as 2 times 7. Then what about the inverse of a third? So I'm looking for a number which, when multiplied by 3, then divided by 17, will give you a remainder of 1. So I claim that this number is 6. 6, why is 6? So 6 times 3 is 18. 18 divided by 17, the remainder is 1. So again, this is 1 times 6. And that gives you this. That gives you 14. Of course, you're finding those inverses using the extended Euclidean algorithm, or we are also using the code. So you are writing a code and then using it to do the inverse. Of course, it's always good to know how to write the code, because we'll be then dealing with very bigger numbers, not smaller ones like the ones we are using in the examples. We're dealing with the large numbers. So you only learn the extended Euclidean algorithm to use it to write those codes. Otherwise, you cannot do it manually for bigger numbers. Now, so we've now discovered that this number on Montgomery, this code, this point will be mapped to 0.164. No, 14.6 on the short Weierstrass. So this will be mapped to 14.6. So it's mapped to this. So it's mapped almost to the last point. So you would not have guessed that. Anybody will not have guessed where to be mapped to until you know how to do it. Now, so that is how we convert points on the Montgomery to points on short Weierstrass. That formula, once you have that formula, you can always do that. Now, let's see whether we can convert them back. The points we got. The first point, 0, 0, had been mapped to 8, 0. So we want to see whether if you have 0.80 on short Weierstrass, whether you can get the point on Montgomery. So that means you have to find S using the formula we explained above. Then you must also find Z0. And then you've been given a 0.80. So in our question, our S we had found to be 15. And then we are converting 0, 80. So our X is 8. Z0 we are also found to be 8. S is 15. And Y is 0. Now, so this point is easy here. This will be 0 times 15, which will be 0. And then this will be 15 times 0, which is again 0. So you can see that if you've been given 0.80 on short Weierstrass form, it will be mapped to 0, 0 on Montgomery. To be mapped to 0.00. So the inverse works. So just applying the inverse. Okay, well, the other point we had was 16.4. Let's see whether it goes back to 5.5. Our S is 15. Our X is 14. Our Z0 is 8. Our S is 15. And our Y is 6. And we are doing this mod 17. So at every time we have to remember that. The first bracket here gives us 6. So you have 15 times 6. And the second bracket here is 15 times 6. So what is 15 times 6? You can use your calculator and then divide by 17 to get the remainder. Alternatively, 17 and 15 are very close. You can just call it -2 times 6 and then -2 times 6. So -2, of course, this is -12. And this is also -12. They are doing it mod 17. This will be the same as 5.5. -12 mod 17. So if 17 were to go into -12, you go there -1 times, and the remainder will be 5. You go there, if 17 were to go into -12, you go there -1 times. -1 times that will be -17. When you subtract this, the remainder will be 5. So it's 5.55. 0.55. So you can see we've been able to convert a point from short Weierstrass to Montgomery, and then a point from Montgomery to short Weierstrass, and so and vice versa. And we have those formulas for doing that. So that is how we do it. So it's important you know how to do. And we have already said that we are doing this because we know that if you could be having the short Weierstrass, and because you want to work on a secure form of elliptic curve, you want to work with the Montgomery, so you convert the short Weierstrass that you have to Montgomery and then use. So of course, you can also convert the points. You can convert the points. And that is what is very important. Even converting those points is always what is most important. Because if you have a sentence, for instance, and you want to encrypt that sentence you have to convert to a point. And this point is the one you'll be then encrypting and decrypting. So that means if I have a Montgomery point, a point on short Weierstrass, and I can convert it to Montgomery, so that if I have a sentence, I can convert to that point. Now, so the Rust code that I've been referring to, this one converts a point from short Weierstrass to Montgomery. Then, of course, we have one that will then converting from Montgomery to short Weierstrass. I was not able to merge the two codes together because if you wanted to convert from Montgomery to short Weierstrass, you're giving it a point on Montgomery. And then you're giving it A and B. And it's doing that for you. So I thought that this one will have its own code, and the other one will also have its own code. Now, so I want to convert a point from Montgomery to short Weierstrass. No, from short Weierstrass to Montgomery. This code is on converting from Weierstrass to Montgomery. Now, so if I want to do that, let me just recall what I need. First of all, the short Weierstrass equation, I have it. Supposing the one I have. So I have this, and I want to convert a point, let me say point XY to Montgomery. So that means this code, I must feed it with A, I must feed it with B, then I must feed it with this point, of course, under the mode that I'm working with. And then the formulas. One of the formula I wanted to get S. So I must give it a formula finding S, the scaling factor. And then it must also be able to get a solution to this polynomial. So if I've given it Z cubed plus AZ plus B, she'll be able to equate to 0 and give me Z naught as the root. Must be able to give me this root. So of course, using this root, you'll then be able to give me S. And S will be 3 multiplied by Z naught square plus A. So this formula I'm giving it to use it to get S. Once it gets S, I must give it the formula for finding the value of X and Y. So those are the things we'll then be looking at. And you saw at some point, I was able to calculate the inverse of what was in the denominator. And that you must also give it, that you must also give it a code. You must write a function that will be doing that, finding the inverse of the denominator. Okay. So for it to get the inverse, and this is the code that will be helping it to get the inverse. And what has it said here? You find the mod inverse of a value A, for instance, which is a big integer, and you're giving it a modulus. Let's say modulus is 7, also is a big integer. Be working with big integers. So if it wants to get the inverse of A or X, first of all, we must know that it's using the extended Euclidean algorithm, finding the extended Euclidean algorithm of that A and the modulus. And then it says, for it to do this, it checks if the GCD is not equal to 1. For instance, 7 and 14. The GCD of these two numbers is not equal to 1. So if it's not equal to 1, it means that these two numbers this number has no inverse. It means this has no inverse mod 17, mod 4. That's why it says, if the GCD is not equal to 1, then there is no inverse. That number has no inverse. Else, meaning that if the GCD is 1, then you'll get some value, X, as the inverse of 7. In this case, let me talk of now P, our P being 17. So if our P is 17 and 7, these two numbers, the GCD is 1. And therefore, its inverse exists. And let's say it's X. Then you reduce this X mod 17. So why are we adding mod 17 again? Supposing the answer here was negative. Supposing the answer here was 12, negative. So you're adding mod again to get a positive value. That's why this one is there. And then, supposing the value that you get here is now positive and is bigger than 7, it's bigger than 17, which is our mod, you reduce it again, mod 17. So you reduce it again. So this is the part that will be doing the inverse, finding the inverse. And the inverse, when are we finding it? We are finding it in cases where we had a fraction. Cases where you have with a fraction, that denominator, you have to get the inverse of that denominator. So this is the part of the code that is doing that. Let me just repeat, we are using the extended Euclidean algorithm and want to find the inverse of a value. Let me say A, and the mod, let me say 17 in this case. And we are saying, for us to get the inverse of A, this part says that A and 17, their GCD must be 1. So if the GCD is not 1, then there is no inverse of A. A has no inverse. Else, in other words, if the GCD of A and 17 is 1, then there is a value X, which is then the inverse of A. There's a value X that is the inverse of A. So that part, that is its wrong. And you have seen a case in our example above, we saw cases where finding the inverse was very important, and we did that. Now, after that, after finding the inverse, no, in fact, here we've not found the inverse. We just said, we're just saying that if the GCD is not one, if the GCD is one, then there is some inverse. But then we come here and find the inverse. We come here using this code, the extended Euclidean algorithm, the one we called upon. So here we were just calling upon it. We were just calling upon it, and it's down here. And once you call upon it, it does the inverse for you. You call upon it there, and once you call upon it, its role is to do the inverse. Now, how does it do the inverse? How does it do the inverse? So given two values A and B, given two values A and B, let me use P, where P is our mod. How does it get the inverse? So it uses the extended Euclidean algorithm to write the GCD of A and P in the form AX plus PY. It uses the extended Euclidean algorithm to write the GCD of A and P in the form AX plus PY. So where this X will then be the inverse of A. This X will then be the inverse of A. So that is what it does. That's what it does. Using the extended Euclidean algorithm, the one I used there, while you begin by writing 1 is equal to this as you move upwards. So that is the one to be using. Now, so it then begins, the code begins by saying that if I have A and B, for instance, and I want to get the GCD of these two numbers, it begins by saying that if B is 0, then the GCD of this is just A. That's what he's saying here. If B is 0, then the GCD is A. And vice versa. What that means is that again, if A is 0, then the GCD here will be B. That's what the code begins by saying. Else, it's now referring to a case where none of the numbers is 0. It's referring to those cases where none of the numbers is 0. So when none of them is 0, then we proceed and find x1 and y1 so that our GCD of A and B, for instance, or let me say that, will be the same as AX1 plus PY1. Why this X1 becomes, I'm not referring to X1 because it will become is a repetitive thing. So this thing is repeating itself. X1 and Y1 will be changing, X2, Y2, and so on until you get that the remainder is 0. Until you get that the final remainder is 0. So that's what it's doing. It's just trying to. The example I gave was we had 17. I remember we had 17, and was it say 15, and we wanted the inverse of 15, and I think we got 8. Was it 8 or something like that? So what it's doing, since none of these numbers is 0, we come here, and now we have 17. We're asking ourselves, if 15 were to go here, how many times will it go there? It will go there once, and the remainder will be 2. And what about if 2 were to go into 15? It will be 7 times, and the remainder will be 1. Once you reach 1 as the remainder, you will now begin reversing as you solve for 1. As you solve for 1. So 1 becomes 15 minus 7 times 2. Now, at every point, we are replacing the remainder. So this was the remainder at this point. 2 was the remainder, and then 1 was the remainder. So we've replaced the first remainder. We've written it in forms of these 2. What about this other remainder? We have to replace it and write it in the form of this other 2. So again, this would be 1 is equals to 15 minus 7 multiplied by, but the 2 is now this remainder, which is 17 minus 15 multiplied by 1. And so on. So that's what this code is doing. So this code is just using the extended, this part of the code, this function here, is doing the extended Euclidean algorithm to find the GCD in form of the 2 numbers, so that from those 2 numbers, it's able to read the value that is the inverse of A. Now, we had S. We had S, and S, what was S? S was the square root of 3 followed by Z naught square plus A. So it means you must have a code that will be doing the square root, because we'll be obtaining square roots. So you must have a part, a function that will be doing, a function, not the code, a function that will be doing the square root to bit. And this is that function. Now, what does this code say? Of course, it's saying that we want to get a square root of a value A, and of course you have mod. And if this value is 0, then of course there'll be the square root will be 0. If the value A is 0, then you return an integer 0. 0 becomes the solution. It also knows that, of course, we know the square root of 1 would be 1, positive or negative. But now it's saying something here. If P is from 2, P is our mod. So it must be from 2, 3, and so on. Of course, it must be a prime number. So it could be 2. 2 is a prime number. 1 is not. 3 is a prime number. 5 is another one, and so on. So if P is a prime number from 2, then the square root will be, there will be some square root. There will be some square root. We'll find some square root. Now, if the value mod, then power, this is a power. Supposing this is P and, okay, this is, these are just U32. These are 32 bits. And this another 32 bits. Now, supposing P minus 1 divided by this mod P would not be equal to 1 if this value here will not be equal to 1, then we enter this loop to perform the square root. And this is how we then perform the square root. So that is how the code will then be performing the square root. Yeah, of course, it begins by letting Q be P minus 1. This one is just a U32. That means we are not looking at the negatives, just looking at the positive values and so on. That's why we're using U. And we let it be mutable. And then let S, of course, we talked about S. We let it be 0. That's what we want to get. We want to get S is equals to, S was this. What was S? It was 3 Z naught square plus A. And then you're getting the square root of that. No, not the square root. The square root and then the inverse of the square root. So, but what we began with, first of all, is just find the square root. Then this up there, we've shown how to get the inverse. Up there, there's a function for doing the inverse. So at this point, we're just finding whatever is inside the square root and then find the square root. Once you've found the square root, there's a function up there that will be getting the inverse. So that function will then perform its role when that time comes. Okay. I've included notes for explanation of whatever is happening at every point here. Then we have another function. The function of finding the square root is a bit longer because there are various steps for finding the square root. But after that, we need to transform from short Weierstrass to Montgomery. So we have to give it again those functions for conversion. So this is where it now begins. So you must give it the point on the short Weierstrass, the x value of the point, and the y value of the point. Supposing I'm talking about 2, 3, we're giving it the x value, and you're giving it the y value. Then supposing our short Weierstrass equation is, this just, I'm just supposing, I've not checked whether this is an elliptic curve, I've not checked. Supposing this is the curve, just supposing. Of course, we have not checked whether it's an elliptic curve. So then our A will be this, which we will give it. And our B will be that, again, we'll give it. And then let's say you're working mod 17. Again, you're giving it P. we're giving it P. Then after giving them that, after giving your code that, you now want to give it formulas. As you write the codes, you give it formulas for performing S, for formula for solving the polynomial to give you the root. And that's what I began with. I began with find a root for the polynomial. So this is the part that defining that root. So this one, I used a method where it's using brute force, where it's trying each of the values to see which one is a root. Of course, it's not very easy to solve that. So you have x cubed plus 2x. Let me say plus 7 is equals to 0, and you're doing it mod 17. The easiest way I thought was to use brute force, where it's trying all values mod 17, so value 0, 1, 2, 3, up to 16. It's trying each of them to see which one will give it 0. So it tries 0, 0 cubed plus 2 multiplied by 0 plus 7. This does not give us 17. Tries 1 until it reaches to a value that gives it 0. So that value is the root it's then looking for. So that is brute force method. It's trying each of the values to see which one will give it a value 0. So that's what it's saying. And let Z naught, and then you enter the loop. And then it's trying every candidate in the range 0 to P. It's trying every candidate in the range 0 to P. And if that candidate, let me say candidate is 0, if that candidate cubed plus A multiplied by that candidate, then plus B, if this candidate is if the value gives you 0, if the value here is 0, then it means you come out of the loop because you've just obtained the candidate. You obtained the right candidate. But if the value is not 0, if the value is not 0, you try another candidate. You try now 1. You try now 1. And see whether you get 0. So if you find that 1 replaced in that equation doesn't give you 0, you try another candidate. So you continue trying candidates until you get one that gives you 0. So if you get one that gives you 0, you break the loop, and so it means you found the candidate. You can now print it. You can print that candidate. So that is how that is the function that is finding the value Z naught. And that is how it's finding it using the brute force method, where it's trying each of the values to see which one is a root. Each one is a root to that polynomial. Now, after finding the root Z naught, you now want to find S. And S, the formula is the square root of 3Z square plus A, then the inverse of this solution. So that is now the formula I want to give it. This is the formula I want to give it so that you get S. So I've said let S squared, I've said let S squared be, of course it will be this 3Z naught plus a. So when you take the square root, when you remove the square root, you see what we have is this. What we have is this. Plus a. So I want to first of all leave out the square root, the inverse part. I want to leave the inverse part, for instance. First of all, leave out the square root part. No, not the square root, the inverse part. I want to concentrate on this. So this, to remove the square root, you just have to write a square will now be 3z naught square plus a. So that is the part that is here. Let s squared be 3 multiplied by z times z, that is z naught times z naught, which means z square, then plus a. So you are doing this mod p. The answer that you get, I told this, I say I had found some problems doing this. So I asked it to print it so that I verified whether it's getting the right S, whether it's getting the right S. So you can omit this print. This print was, I just put it there to verify for me if the S I was getting was correct. If the S I was getting, if the S squared I was getting was correct. Because at some point when I was doing that, it was giving me a wrong value. So I wanted to find out where is it going wrong. So that is why I asked it to print this one. You don't need to print it. You only need to get S squared. So once you get S squared, you can now get S by getting, so let me say you've got an 8. So that means S will now be the square root of 8. So S is now the square root of S squared. S is now the square root of S squared. That's what I've just said here. So if S squared is 8, then S is the square root of 8. So again, it will do that. Now, what about the inverse? Now S, we're supposed to get the inverse because that is what the formula was about. The formula was S was supposed to be square root of something. But we already worked with S. So we want the square root of S. Not the square, the inverse. The inverse of S. So the inverse of S, we now call upon the function above that was performing the inverse. To get the inverse of S, we call upon that function to do for us the inverse. So again, you can ignore this and ignore this. I just put them here to assist me know where the error was coming from. Because I was at some point I was getting the values I was getting physically. You see, the values I was getting by calculation were not agreeing with the values I was getting by the code. So then I wanted to find out where is the problem so that I look at my calculation value and the value of the code and see if they agree for S squared and for the inverse and so on. So when you find out where the problem is, you can always rectify the problem. Now, so once you have S, now what follows is just to now find the point. You can now find the point, but although I wanted it, first of all, to give me the values of A and B of the Montgomery, but this is not very important on the current topic. The current topic what we are converting are converting points to points. But I wanted it to give me also A and B, because I really wanted to know where the problem was when I was doing that. Now, that is how you do it. That's how you do it. You can ignore most of these prints, but what was I printing? You can ignore most of this. what I wanted was just the X value and the Y value of the new point. This one was just again a way of trying to find out where the error was. Now, so my short Weierstrass points, the equation had A and B, and then P there, and the value of X and the value of Y. And this is the same thing we've done manually. So I wanted to verify whether this point will move to 5.5. That's what I wanted to verify, if it will go to 5.5 as we had gotten in our physical calculation. Okay, let me just share the code therefore, and then we run and see. Right, so this is the code. I had put a lot of prints, print, just to, as I had already said, to find out where the errors are coming from. Okay, so this is where you input your values. The A for the short Weierstrass, then the B, and then the mod, and then the point XY. And then you want to run and see whether it gives you a point on Montgomery. When you run this, gives you, you can see this is what I wanted. I wanted it to give me all this because I was finding some errors. So it found for me the value of Z0. It gave me the square root of S. And then it gave me, no, the square of S square. Then the square root of that, it gives me. Then the inverse of S, it gives me. And then I ask for value of X of Montgomery and the value of Y, so that this is 0.55. 0.55. And then I ask for the A coordinate, no, the A value for Montgomery and the B value for Montgomery, which is 15.3. So again, it gives me that. But the most important thing was this, is what I wanted us to calculate. So this is the code that then gives us, let me just share it. You see it from the beginning because of the recording, so that at your own time you can try and see how you can improve it in some places or customize it. Okay. Now, this one converts from short Weierstrass to Montgomery. And I also have one that converts from Montgomery to short Weierstrass. And here it is. This will be converted from Montgomery to short Weierstrass. This one we've not explained because of time, but you can see you've given it the Montgomery A and B values as 3 and 15. And then this is the coordinate you want to convert, 5.5. And you want to see whether it gives you 14.6 for short Weierstrass. And it gives you the value of X as 14 and the value of Y as 6. And again, this is, so you can see it from the beginning, so that at your own time you can see how to. So this is where I input my modulus. You can put your modulus mod P here. So you can customize it or try to improve it. So that is what I wanted us to look at today, how to convert points on Montgomery to points on short Weierstrass and vice versa. I've included, in my notes, I've included how the codes work so that you then look at the code and look at every part, the function, how the function will be working. You can look at every part and follow. Thank you.